So in this problem, we're given this shell here with a volume density of P here, and it's A over R. We're trying to figure out what A is. We know that this shell is a uniform E, and there's a charge in the middle here that's giving us some trouble, and there's two radiuses we have to deal with. So we can solve this by using Gauss's law and drawing little imaginary shells everywhere and just trying to see, okay, it's supposed to be uniform E. So if I draw a shell here, or if I draw a shell here, or here, doesn't matter where I draw it, they're always going to have the same E, right? All right, so let's try to consider that when we use our equations, because, let's see. We have EA cosine theta is going to be equal to Q enclosed divided by the epsilon naught thing. And the Q enclosed inside of any one of these spheres, let's say it was this one right here, you'd be getting all of this charge that was inside of that sphere, and you would be dealing with the Q inside of there. So let's consider that. This is inside is going to also be like the small Q that's in there, and then plus, or I guess we'll make this one the Q, and then plus that Q. Okay, so there's two Q's that we have to deal with inside of here. There's the Q that was given, 47.7 e to the negative 15 coulombs. Okay, so that's just basically a positive Q that's in there, and it's a very small positive Q. But anyway, over here we could start thinking, okay, so this E is supposed to be the E of this, and we're going to try to figure out what's the charge inside, because we've already know this charge. We need to know this Q, because we have this density and Q, and we know those two are related, because we know that Q is supposed to be equal to P times V. And one very important clue that we can see in this particular thing is P is supposed to be equal to coulombs over meters to the third. We know this is supposed to be meters. And so this particular variable, A, is going to be coulombs over meters squared. Now, if we know something about density, we know that that is actually just this symbol then, because that's what that would be. So just keep that in mind as we solve for this. So now we have Q equals PV. And the volume for whatever we're looking at here, we're going to start at radius A, and then we're going to go to the next radius, which I'll call that G. And I want to keep track of these variables, because some of these variables are going to be changing and some of them are not going to change, right? So, you know, this one would have a G1, a radius of 1 there. This one would have radius of 2, and this one would have a radius of 3, right? So you could sort of see at these different points, you're going to have different radiuses for that particular G value. And then the volume is supposed to be the integral from, we'll start at A, okay, and then we're going to go up to the G. And then we have the surface area of a circle is supposed to, of a sphere is supposed to be 4 pi r squared. And that's what we're going to plug into there, dr. So we know that the Q, only this Q, the small q, is supposed to be equal to P, which is A over R, but A is actually just this, so it's supposed to be this over R. And then let's integrate this whole thing also, because we're multiplied by the volume, so we'll go from A to G here. I made that a little sloppy, but it's okay. Anyway, 4 pi r squared dr, and then these r's are going to cancel, so we'll get another integral, A to G. And let's try to actually pull out the constants as we do this as well. So we'll go 4 pi is a constant, and this is a constant as well. So then we're just going to get the r dr, which is the r squared, divide that by 2, but that's going to go from, you know, G to A. Okay, so we can kind of do this stuff in one step. We're going to get that comes out to be 2, so we get 2 pi this, and then let's just multiply this out. So g squared minus a squared. And this is our q, a small q. And then we also have big Q. So let's go now into our E equations. So we'll go, I suppose we could solve for E. So E is going to be equal to little q plus big Q. And the big Q is 47.715C. And then we have the little q, which is supposed to be 2 pi, and then the density, g squared minus a squared. And then we can divide that by epsilon naught here. But we could also move over, obviously cosine is going to go away, but we can move over the area there. And area for this sphere is supposed to be 4 pi r squared. But what is the radius that we're using? It's g, because that is the sphere that we're looking at. So, like I said, I want to kind of keep track of, this is the Gaussian sphere. Remember, this area is the Gaussian area. So that is why we're using g for this radius. So, say 4 pi g squared. And I'll mark these g's that we're looking at, because this is really the variable that's gonna be changing. So every time that we create a new Gaussian sphere here, this is a different g, and it moves over here, this is a different g, and it moves over here, that's a different, you're gonna sort of get different e's, right? If you have changing variables, you're gonna get different e's. How are we gonna make this become a constant if we have a whole bunch of variables? Because obviously, as we change the variable in this, it's gonna change the e value, right? So it's not uniform, but it's supposed to be. So one way we can make it be uniform is to have this just equal to 0. But I mean, maybe that could work, but maybe that could not work. Let's see if we can try to simplify this, because I see some g squareds everywhere. So what if I made this be like, put everything, expand the top. So let's try to expand the top, 4.7 e to the negative 15, and see if there's anything that can cancel out. We'll get the g squared, and then we'll go minus 2 pi, this thing, a squared. And then we'll divide that by e naught. But notice we have one denominator. So if we have one denominator and we have 3 numerators, that means we can actually separate that out and create 3 different expressions here. Okay, so now maybe something will cancel out. I'm going to highlight these g's again. All right, so obviously these will go away. And that means that we might have a constant value somewhere in this. We do see we have all these variables over here. And this is supposed to be equal to e. Now we have a constant in here. And so if these two were to go away and become 0, then we would just be left with the constant. And so every time that we change the g's, it doesn't matter. These are just going to cancel out and become 0. This plus that equals 0. Then we just get a constant e. So let's do this operation. All right, 4.7 or 47.7. I keep making that same mistake. It's so funny. Divided by 4 pi g squared minus 2 pi this thing a squared divided by e naught 4 pi g squared. That's supposed to be equal to 0. Well, then that means that they're equal to each other then, right? So now, g squared, oh, I guess the g squareds are going to cancel. That makes sense because they're not supposed to matter. If we change the g's, it shouldn't matter. Those 4 pi's will cancel, this will cancel, and we're left with a pretty simple expression. Density is equal to 47.7 divided by 2 pi a squared. And if we plug that into our calculator, 47.7, 15, divide that by 2 pi times the a squared, which is 0.0213. Well, there we go. We get our answer. Nice. So, yeah, this was a little bit tricky to kind of capture, but again, it's the changing variables that we need to look at. What's changing, what's not changing, and draw a whole bunch of Gaussian spheres and see what happens at those points.